Hello and welcome back, everybody. Here we're going to look at the diagonal coordinates theorem. Let's read what it says first and then we'll talk about it. So if A is diagonalizable, meaning it can be written like this, an invertible matrix times a diagonal matrix times the inverse of that P. And if we write P in terms of its columns and label those columns B1 through BC, and we could also think of that matrix, like the matrix P here and the list of vectors B are basically the same thing. It's just that we're thinking of B as a list of vectors that is in fact a basis. And it's a basis because you could think of the buy two get one free theorem that says we have the right number of vectors to make a basis of RC, and the columns of a invertible matrix are always linearly independent. So there's a lot of ways you can see that that's a basis. Now, for any positive integer n and any vector y in RC, this gives us this maybe slightly gnarly looking equation if you're not used to coordinates. But basically, it relates the coordinates of a to the power n times y with the coordinates of y itself. Now, it turns out the proof for this is actually kind of simple. It's mostly changing notations around a bit. Let's try to get our heads around it, and then we'll look at an example of it. But first, for the proof, let's say that the b coordinates of y is this vector x1 through xc. What does that mean? Again, hopefully you reviewed 1.6 and 1.7 and you feel good about what coordinates mean. This is just another way of saying that these coordinates, x1 through xc, those are the weights that you would use when doing a linear combination of the b vectors to get y as a result. So the coordinates, this coordinate vector, is like the solution of this vector equation, where y is the thing you want on the right-hand side. So that's what we're talking about here. And we're going to think about what is like d to the power n times that in a minute. But let's also think about like what we're trying to get. We're trying to get a formula for a to the power n times y's b coordinates. Right? We want to know what is this coordinate vector. But what does that mean? That means we want to know what are the weights of the basis vectors, so that when you do that corresponding linear combination, you get a to the power n times y as a result. So that's what we're trying to figure out, is how to get a to the n times y as a linear combination of the basis vectors. And the basis vectors being the columns of this invertible matrix P. Okay, so let's think about what a to the power ny is and see how we can write it this way. Well, instead of a to the power n, let's think of its diagonalization version. P times d times p inverse to the power n, and then that times y. Well, we just saw previously here, the same principle applies. You could write this out n times, and all the p inverse times p's will cancel out in the middle, and you end up getting p times d to the power n times p inverse times y. And what can we do with p inverse times y? Well, okay, remember p has the b1 through bc's as its columns. Well, let's see. I'm going to take this goal here and maybe move it over here, because I want to write this a little differently, this equation. This equation could also be written as b1 dot 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 up to bc as the columns in a matrix times the vector x1 dot 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 up to xc equals y. This is the same thing as P, right? These columns make up the P matrix. So we have P, and then the x1 through xc, that is just the B coordinates of y. Now, we're assuming that P is invertible, so you could just multiply both sides of this by P inverse to cancel it out and move it to the other side. So just like if you want to solve this vector equation, or if you want to write it as this matrix equation, you can to find the B coordinates of y, you can solve it by multiplying by P inverse on both sides. And oh, hey, that is P inverse times y here. So this, in other words, this thing we're trying to find is P times d to the power n times the B coordinates of y. In other words, this x1 through xc vector here. So that is going to make this have a much easier way to write it out. Actually, let's just expand this whole thing. Let's write out the P in terms of its columns. And then d to the power n, hey, we got a nice formula for d to the power n a minute ago from the previous video. And then the B coordinates of the vector y, we said is this vector x1 through xc. And we can see what's going to happen when we multiply this diagonal matrix times this. Like we're going to do x1 times this column, x2 times the second column, xc times the cth column, and that's just going to be x1 times d1 to the power n, yada yada yada, up to xc times dc to the power n. And then we're doing this matrix times this vector. What we get is a linear combination of the columns of P, which are the B basis vectors, that looks like so. And let's remember, what are we trying to find? We're trying to find the B coordinates of this. Like again, this whole thing is still a to the power n times y here. And what do we have? Oh, we have the linear combination of the columns of P that we wanted, and we can see what the weights are. Thus, the B coordinate vector of this thing is, well, we have it here already. It's the x1 times d1 to the power n, yada yada yada, up to xc times dc to the power n. And we just showed here, we're kind of going backwards now, that this is the same thing as this diagonal matrix to the power n times the y coordinates of B. But yeah, that is d to the power n times the x vector, which is the B coordinates of y. Did I say y coordinates of B? Yeah, B coordinates of y. So there we go. That proves the theorem. Now, this might just feel like an awkward change of notation that doesn't really show you anything, but I believe that when we look at it in terms of a graph, it really tells you what the power that diagonalization has. Let's look at this example 4. So what we have is this kind of random looking matrix A with columns 1.51, which is like over here, and another column is 0.51, which is over here. So the columns of A itself actually have nothing to do with this grid. I mean, they have something to do with the grid, but they're not shown on this picture. But that's A. It can be shown that if P, this matrix here, we're going to label the columns as B1 and B2. If P is that and D is this diagonal matrix here, then A can be written as P times D times P inverse, that it is diagonalizable the way we want. And that means the diagonal coordinates theorem applies to this. Now we're going to think about doing powers of A times this vector x0 here. And x0 is 1b1 plus 1b2. In other words, x0 is right here. Because I want 1 in the b1 direction and 1 in the b2 direction. Okay. Also, what are the b coordinates of x0? Well, it's going to be what do you scale b1 and b2 by to get x0 as a linear combination? Oh, that's just 1, 1. Okay, so we have that. Now let's use the diagonal coordinates theorem to plot x1 and x2, because x1, according to this, is going to be equal to a to the power 1, which is just a, times x0. And we could actually just like calculate that out, but I want to use the theorem to see how can we get the coordinates of this in terms of the B1 and B2 grid. In other words, what is the B coordinate vector of x1? Well, let's see. What does the theorem say about this? It says this is equal to the diagonal matrix D to the power 1 times the B coordinates of x0. And hey, we can calculate that. The diagonal matrix has diagonal entries 2 and 0.5. And we already got the B coordinates of x0 are 1 and 1. And when you multiply this, you're just going to get 2 times 1 and 0.5 times 1. Now, this doesn't mean the vector 2, 0.5 right here, because again, we're talking about B coordinates of this. So these are where do we go in the B1 and B2 directions along these axes. So the B1 coordinate is 2. So this is 2B1 right here, twice as far. And then the B2 coordinate is 0.5 times B2, so half as long. So the actual point x1 is, I don't know, approximately 1.5, 3, something like that. Let's see what happens if we do this again. The B coordinates of x2 will be d squared times the B coordinates of x0. And that's actually just the same thing as multiplying the d times the B coordinates of x0 that we had before. So in other words, that's just going to be this diagonal matrix d times 2, 0.5. That will be 4, 0.25. So that means we're now doing 4 times B1, which is over here, plus 0.25, a quarter of B2, which puts you right here. So this vector is x2. Now, the general pattern here looks like this. The B coordinates of xn, which is still a to the power n times x0, is going to be 2 to the power n 0, 0, and 0.5 to the power n times the B coordinates of x0. This is exactly what the theorem says. This is that d to the power n part. And we know what the b coordinates of x0 are. It's just 1 and 1. So this just ends up being 2 to the power n times 1 and 0.5 to the power n times 1. And so every time you multiply this by a again, you're doubling the b1 coordinate, moving away from the origin exponentially, getting closer to being a multiple of b1, because also the b2 coordinate is also getting smaller exponentially at the same time. Now, this was the way it worked with this like particular x0. But what if you had a different x0? Let's try something else. Let's say x0 is down here. This one is x0 is just negative 2b2. Its b1 coordinate is 0 because you don't go that way at all. So x0 itself is negative 2. x0 itself is 2, negative 4. Those are its like regular old-fashioned coordinates. But its b coordinates are 0 and negative 2 because x0 is equal to negative 2b2. Okay, so this is going to work the same way it did before. The b coordinates of xn are going to be 2 to the power n times 0 and 0.5 to the power n times negative 2. So, for example, the b coordinates of x1 are still going to be 2 to the power n times 0. That doesn't go anywhere. But 0.5 to the power 1 times negative 2 is negative 1. So that's right here. If we keep going in this direction, we're still doing 2 to a power times 0. That's still 0. 0.5 to the power 2 times negative 2 is negative 0.5. So where we get is negative 0.5b2. Likewise, when we multiply by a again, or which is doing the same thing as raising the power of 0.5 once more, we're going to get negative 0.25. So now x3 is going to be at negative 1/4 b2. So you can see what's happening. It's just like asymptotically getting closer to the origin there. And you can imagine that any multiple of b1, like if you had something here, this was your x0, the b1 coordinate would get multiplied by 2 and multiplied by 2 again. But you'd be doing 0 times the b2, or which ends up doing 0.5 times that coordinate, which is 0, which doesn't do anything. Let's see. Turns out if you start like over here as your x0, the b2 coordinate is going to get smaller by half. The b1 coordinate will get bigger by half. And you end up moving out along this hyperboloid thing. Maybe you can imagine if you started on this hyperboloid, you would keep going this way, and so on. So yeah, this shows how you can think of raising powers of a matrix, as long as your matrix is diagonalizable like this, as getting you either closer to the origin or farther away from the origin, depending on what the diagonal values are, and doing that in the direction of the columns of the P matrix here. All right, we'll look at a few other examples of how this could work with like different kinds of entries in the diagonal and different kinds of vectors here. And we'll look at 2 more examples in the next video. So I'll see you then.